Okay, we are about ready to start a new chapter, chapter 11, on sequences and patterns. This first section is on sequences and series. So let's look and see what our learning goal is today. We want to be able to find the different terms of a sequence in any way possible, and then also evaluate the sum of a series expressed in sigma notation. So let's go ahead and look at the first one. Remember that there are all different types of series. Series might be a list of ordered numbers in some way, shape, or form. So if you looked at these, and I asked you, what is the pattern in each of them? Would you be able to find them? So study them each for a second. Starting the first one, 2, 4, 6, 8, 10, and so on. 1, 2, 4, 8. So you're looking for patterns in each of these sets of numbers. Lists, sequences, we'd like to call them. So let's see, looking at them briefly, if you can come up with some of the patterns we're looking for. So in our top row, did you get that it was nothing more than an add 2 every single time? In the second one, timesing by 2. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. In the third one, the list is definitely increasing, but what'd you find? It was a divide by 4. Negative 64 divided by 4, negative 16. Negative 16 divided by 4, negative 4. Negative 4 divided by 4, negative 1. So you're good there. The green star, 1, 1, 2, 3, 5, 8, 13. For some people, this one was tough. Add the previous two terms. So if you take 1 and 1, you get 2. Add 1 and 2 to get 3. Add the 2 and the 3 to get 5. Add the 3 and the 5 to get 8, and so on. And the last one, 1, 2, 4, 7, 11, 16, 22, etc. Looks like you are adding 1, then 2, then 3, then 4. And how do you describe that? You add consecutive integers. Okay, so those are all examples of lists of sequences, terms in the sequences. Those are all going to be important as we move forward. So let's double check. We have some definitions. A sequence is nothing more than an ordered list of numbers. We have talked about an explicit sequence being a way to go directly to your equation. In some cases, we'd like to say directly to your number. If we say we have a recursive list, now the situation there is that there's a repetitive process going on. Like we'll give you the first term, you do something to that first term to get the second. You do that same thing with the second to get the third. So those were our recursive equations. And then now we're going to add a new definition, or two new actually, a series. An expression that indicates the sum of the terms of the sequence. So a series is take those terms that we had listed, and now if we would add them all together, that's what a series is. So look at this. We'll have something called summation notation. That's going to help us with our series. In our summation, we have the Greek sigma listed. We have two index numbers, one that's below it that tells us where to start, and one that's above that tells us where to end. Then, next to the sigma on the right, we have the explicit formula that we want you to use, the one that allows us to get the individual terms, and then you will have to do something to add them all up or generate whatever the question's asking. Okay? So let's go forward and see what kind of questions we're going to have. Oh, prior to that, there's a couple different types of summation properties. So let's look. When we talk about styles and types here, we're looking at if they gave us the sum of two terms. They're saying if we wanted to sum a sum of terms, you could take each term separately. So notice this is the a sub k, and this is the b sub k. So we could do the series, the summation notation on each of them separately, add those together, add those numbers together, and we would get the same as if we had taken the sum all together. Next one is, what if I have a constant? C is our constant, and I'm multiplying it by some values, and I'm doing that for k equal 1 to n. Then a shorter way is to take that c or constant, put it out front, do the summation of that term from k equals 1 to n, and then times it by that c value, and you would get the same result. So those are our examples of summation properties. But we have some formulas. We know if we have a constant term, a linear, and a quadratic, those are ones we can recognize quite easily. So if I have a summation, I want you to take so many constants and add them together so many times. That's just the same as saying from 1 to n, of that constant c, it would just be taking, tell me how many n's you want, or how many c's you want, which would be n times in this case. And so we would just get n times c. So our constant series summation formula is, if I have a constant and I want to add it n amount of times, we would just have n times c. Pretty simple. Now the linear series is a little different. If you have some linear value k, and it could be the expression, 2n plus 3, that's linear. So if you have that linear expression, and you want to add all of the terms in the sequence from 1 to n, so the first 5 terms, the first 6 terms, the first 10 terms, whatever it is, then you can simply take the n value times the n plus 1 and divide by 2, and you should have the sum of all the linear terms in that sequence. Quadratic, similar, but you obviously got to have a quadratic part to it. So you need that squared part, and that would be n times n plus 1 times 2n plus 1, so they're similar, n plus 1, 2n plus 1, the n's are now building, all divided by 6. So we're going to show those examples as we go, but let's start with a couple of real basic ones, and let's highlight them one at a time here. All right, our first one. Write the first 6 terms of the sequence defined by this equation. They want 6, and all they do is want the terms, so we're not adding them together or anything. So if you want to, you could just make 6, let's make them 6 blank lines and fill in those blanks as you go. So, and if we did t sub 1 in our head or on paper, 4 times 1 is 4, 4 plus 5 is 9. Go right on up. T sub 2, that would mean 4 times 2 is 8, 8 plus 5 is 13. T sub 3, 4 times 3 is 12, plus 5 is 17. So you're noticing it's an add 4, add 4, add 4, so if you did that and completed it, add 4, you would suddenly have your sequence. You can check it and see if it agrees. And it looks like we do, other than the 29's chopped off. Okay? So you can just put the numbers in, do the number crunching. Never asked us to add them up. It just said, what are the 6 terms of the sequence? Same thing here. Write the first 6 terms of the sequence. We're not adding them up. This is a different type of sequence. That last one was more of an explicit. You go directly to your number. This one's written in the recursive form. You can tell that by the 2-system equation that we have showing to start with. They give us the first term. And if we read this, it is, I'm going to get all other terms in the sequence by taking 2 times the previous term and subtracting 1. That's how you would want to read this subscript in notation. So if we had t sub 1 equals -2, we can start again with our 6 terms, 6 blanks, and our first term is -2. And t sub n equals 2 times the previous term. Well, the previous term is -2, so 2 times -2 is -4, subtract 1 is -5. Third term would fall into the second equation again. So the third term says take 2 times the previous term. So 2 times negative 5 is negative 10. Subtract 1 is negative 11. 2 times the previous term, negative 22. Subtract 1 is negative 23. You can see how we're filling this in. 2 times negative 23 is negative 46. Subtract 1 is negative 47. And keep going in this fashion. Negative 47 times 2, negative 94, minus 1, negative 95. So you can see you would have the first 6 terms, and again, checking, we agree. Okay. Moving on. Now it says write the terms, then evaluate. Oh, so it's a summation notation. So first it's asking, and it is just a single combination. My equation, my explicit equation is 2 times k. K runs from 1 to 6. So ready? When k is 1, 2 times k is 2. When k is 2, 2 times 2 is 4. When k is 3, 2 times 3 is 6. When k is 4, 2 times 4 is 8. When k is 5, and when k is 6. And so there are your terms. Now you're saying, well, what is that? It says write the terms, and I think we got them. Erasing here. Yeah, there they are. Okay, but it says now the sum. So the summation of those terms means you have 6 terms listed there. What is the summation? You could at this point, because the numbers are fairly small, go ahead and add them, and there's several ways. Here's just one of them. You've got 4 and 6 is 10. You've got a 10 already there. You've got a 2 and 8 is 10, so that's 30. The only number we didn't use was the 12. 30 plus 12 is 42. So we're getting a sum of 42. So when we add them all up, those 6 terms equals 42. Remember that we did introduce a shortcut. So going through this process, the shortcut said 2 times k. K is a linear term. In this case, it's to the first power. You could put that 2 constant out front and just list the sum of those k terms. And you see me doing that in the setup there. So again, adding those numbers however you want to in your head. You got 5 is 10, there's another 10, 21. 21 times 2 is 42. Either way you do that. When it's a small list, you have the choice. When it gets a little harder, bigger, you definitely probably want to use the shortcut in your work. Okay? So that was for a linear combination. 2 times k is a constant times k, and we wanted the summation of all the terms. Next, we say evaluate. This is the summation of all the terms, and this looks like a quadratic, a linear, and a constant term. So if we would take into effect that constant shortcut, that linear shortcut, and that quadratic shortcut, we should be good to go. Otherwise, we're going to have to list all the terms for the quadratic, all the terms for the linear, all the terms for the constant, from 1 to 5, add all those up. That could be, for some people, quite the nightmare. So here we go. Break it up first into its parts. So we're taking the quadratic part out of it and writing it separately. We're taking the linear part out of it, writing it separately, and taking the constant and writing it separately. Didn't put an arrow like on the other ones. So knowing that, we have a 3-part equation to do. They're all, notice, from 1 to 5. So our quadratic formula says take your squared term and take n. Now we have that 4 out front, which is a constant. So let's pull that out because that's like a normal constant. So let's pull that out front. And now n, our n value is a 5. That's the top index. And from there, we'll take that top index number. That's our n value for n equal 1 to 5. N is 5. N plus 1 would be a 6 then, and 2n plus 1 would be 11. So all we did was that shortcut, and it's all divided by 6. So we'll get that number, we'll do the math, we can even do some canceling here, times it by 4, and we'll have the sum of the quadratic part. For the linear part again has a constant term in it. Put that constant out front, and the constant equation says take n, which is your 5 again, and times it by n plus 1, which is 6. So here again we can do some canceling. And then the last one is the constant term. We have basically 5 sevens. 5 sevens is just n, 5, times our constant, which is 7. So doing the math, looking at that, we've got a little arithmetic we can do. But make sure you do some canceling along the way, because this would now be fairly easy to do in your head. If you've said 5 times 11 is 55. 55 doubled, 110. Doubled again, 220. Could do that in your head. Here you could cancel and get the 3. 5 times 3 is 15, times 2 is 30. 5 times 7 is 35. Then you're looking at those three numbers. Add it all up. The sum of the terms in this equation added up, going from 1 to 5, when k is 1 to 5, would be the value 225. That's what we're looking at. So there's the work that you were supposed to see on that one. And that's all we're going to need. Really specifically, you're going to use those constant, linear, and quadratic summation shortcut properties to help you work through the math. If, however, like on the one example I did, if it's fairly easy to do without the shortcut, numbers are small, go ahead and just add the terms up. But after a while, if you're doing for k summation of 1 to 50, you're definitely not going to want to do something like that in your head. Okay, so practice those. Bring any questions you have with you to class.